All right, what's the disadvantage first of public key encryption systems? Okay, I'm going to start with you. Go on. He's not with me. He doesn't want to be with me. What's the disadvantage of public key encryption systems? What's the problem with them? It's very slow. And what's the advantage of public key encryption system over conventional encryption? The key distribution is easier with public key. Give me another. Nikita, another advantage of public key encryption system. Okay. Any other advantage, guys? Public key encryption system. Come on, you should have 5 or 6. No problem. 7 or 8 on the outside. Number of keys is less, is smaller. Easier to distribute public keys. Kamush, easier to distribute. Number of keys is less than in a system, less than the number of keys in a conventional encryption. No need to meet face to face in order to exchange the keys. And no need to trust whoever you're communicating with and having secure communication. And it's based on a mathematical theory. It provides authenticity, non-repudiation, and digital signature. How does it provide authenticity? How can we provide authenticity using public key encryption? Any idea? How do we provide an authentic message? With whose private key? Sender or receiver? Sender's private key. And it's decrypted by the receiver using what?
Public key for the sender.
The sender's public key. Right, and how do we provide confidential messages? How do we use public key to send a confidential message? Yeah, okay, thank you. So encrypt the message using the receiver's public key and decrypt it using the receiver's private key. All right. How is non-repudiation? How do we get non-repudiation? What's non-repudiation?
Where the sender or receiver cannot deny having sent or received.
When the sender cannot deny that they sent a message. So how can they not deny? When a sender sends you a message and they say we didn't send it, no, we know, we say you did send this, we have the proof. What's the proof? How do you prove that somebody actually sent a message? Yeah, how do we prove that? How do we prove a message? You sent me a message and you say I didn't send it. I say, no, I have a proof.
If you can decrypt the message with the public key of the sender.
Because this is the proof. We can take the message and your public key, you sent me a message. If it deciphers that message, that means your private key was used to encrypt the message. That's a proof. There's no other key in the world can decipher it. If you encrypted it with your private key, you're the only person in the world that has that key. and we can undo that, whatever your private key does with your own public key. So that's the actual proof, and that's why we can have non-repudiation. And how can we distribute public keys in public key encryption systems? How are public keys distributed? Using public key certificates. How do we distribute a key in public key certificates? How is it done?
The key is sent to the control center.
Okay. How does the certificate actually help distributing the key? Any idea? What's in the certificate? ID and the public key, and some other information, but these are the two most important pieces of information. Your ID, your name or your company's name, and the public key. That means this public key belongs to this party. It doesn't say you are a good party or a bad party, just this is your public key. Right, but I can have, my own certificate and I send it. I write my own public key and my name and I send it to you. How do you know this is a good certificate or not good certificate? Why does the certificate use a good way of distributing it? What makes it good? What makes it, trustable? How do you know? If I send you an email and I say, okay, this is me, Faheem, and this is my public key. Is this a good one? Good enough? Maybe it's not my public key. Maybe it was sent by someone else pretending to be me and telling you this is my public key. So, but using the public key certificate, we know for certain this is your public key. Why?
Certificate is given by CA, which is part of the trust.
Yeah, because the public key certificate is issued by a trusted public key certificate authority. There's an organization that we all trust and we all know their public key. They are the ones who are issuing the public key certificate, not an ordinary person who might falsify it or send you the wrong one. But now, how do you know this certificate was issued by that certification authority? What stops me from saying, hey, I am, the star public key certificate, I am, which I am not. And here's the public keys for this person. Yeah, it could be a false certificate. So why do public key certificates work? They can never be falsified. How do you know this certificate that you got is a true, good certificate, public key, or a bad certificate? How do you know? If I send you my certificate, how do you know this is a good or bad certificate? How can you verify it? It has an ID. Yeah, that's my name, Faheem, and public key. But it was really a false certificate. How do you know this is a false certificate?
Authentication check.
How? How do you authenticate it? That's the question. How do we authenticate? If somebody sends you company from the other side of the world, different country, they sent you, they said, we are this company, ABC, and here's our public key.
Check the identity.
The identity says ABC. It is the correct identity, like we think. How do you know this is a good public key certificate? It's signed by this trusted authority. Then you can decrypt it using the public key of that authority. And if it does, then it was issued by that trusted authority. Not anyone else can produce it. If you doubt, then use the public key authority to decipher it. And it should have the correct ID and a public key. And if you're still in doubt, you can contact that authority. And also check the revocation list in that authority. maybe they did issue it last month, but now they've cancelled it, revoked it, so check it out. Now, back to my original question. How secure is RSA? How can RSA be attacked? There isn't, a good way of attacking RSA. But what they do is they kind of work out, if you give them a key or they want to maybe reduce the range of where your key is. They know it's a number, but they cannot do a brute force, it's impossible. So they try to narrow down the numbers, the range of numbers. And how do they narrow it down? They take it and they calculate how long, for example, did it take to encrypt a message. And remember, encryption in public key is multiplying a character by itself as many times as what the E is or the D, the number. You multiply something by itself, say 500 times, for example. That's how you encrypt every character. Okay, so you give it 100 characters and say encrypt them and measure the time. How long does it actually take to encrypt? And you can get an approximate number of, if you know the speed of your processor and the length of time it took to encrypt a message, then you can work out close enough. You won't get that number exactly, but you say this, it looks like it multiplied by itself 750 times or whatever, 750,000 times. So you say plus or take few thousands. So you maybe 100,000 keys. Say, okay, the key is going to be somewhere in there. It's like an airplane is traveling and it got lost. You say the last call we got about 15 minutes. How fast does the airplane fly? And you can work out approximately where it's going to be. But it could be between 500 miles to 700 miles or something like that. So same with the key. See how long does it take to encrypt or decrypt a message? And then you can work out the range, and you can say, all right, that number is going to be between those two numbers. Let's just now try those, brute force, only those. And that's how it's a way of doing it, but sometimes you can actually increase maybe the messages, but it's possible. And another way is the power consumption as well, to do the calculation. If you know how your CPU, how much power it will consume to do certain, that's reasonably accurate. They can actually work out how much power was consumed to encrypt a message. Then you know how long the CPU was working, and you can get close enough to that number. But you need to have the key, you need to have the message, you need to have a machine and fairly accurate devices to do it. But still, it's still probably one of the best systems around. How is Caesar's algorithm attacked? Caesar's algorithm? That's a different one. Brute force attack. Yeah, that's one way of attacking it. Any other way to attack Caesar's algorithm? Cryptanalysis. Using the cryptanalysis technique to attack Caesar's algorithm. And which one is stronger? Caesar's algorithm or Vigenère cipher? And the reason? So Vigenère is not a monoalphabetic cipher, please. So it cannot be attacked by the brute force attack or, sorry, the other cryptanalysis. Okay. And here's the algorithm to produce the RSA pair of keys. And where's the example? And here's an example with numbers. This is probably the easiest, smallest numbers to use to produce RSA pair of keys. That's, you start with two prime numbers, and 3 and 5 are probably the smallest prime numbers you can use. So they produce the smallest kind of numbers that are used. Okay, I think we have it. This is the question we had earlier on. How could you have a message that's encrypted in such a way that it is confidential and also authentic at the same time, where it needs to be encrypted twice? Sorry. It needs to be encrypted twice, so the plain message is encrypted first time using the private key of the sender's private key, and that message that's encrypted, it's re-encrypted again, this time using the public key of the receiver. And it's sent, so if that's encrypted twice, this one, C2, that means it's ciphered twice. When it's received, it's decrypted first by the receiver's public key. That removes the confidentiality or guarantees the confidentiality, and then it's decrypted using the public key of the sender, who encrypted it using their private key, and that gives us the authenticity of that message. So these are the steps here. I think you're pretty okay, guys. Okay, guys, thank you very much. I think this is all we are having today.